Today we're going to see an exercise in mechatronic systems. We have an example of a system that has mechanical components and also electronic components. So we're going to take a look at this study guide number 5 that talks about this. And let's get started. So let me disappear over here. This is study guide and assignment number 5. You have electromechanical systems. The first topic that you see here says transfer functions, electromechanical systems. So this is a PowerPoint presentation that we have about the transfer functions, and it points to the class notes in this regard. There's a couple of presentations on modeling difficulties, which is another topic that we haven't touched on this yet. When you have derivative causality for elements that have dependencies and also algebraic loops. But the main thing hovers about this topic. What are transfer functions and state space models? State space models we already know. This is the representation of systems in a state space form, meaning the form where we have the matrices A, B, C, D in first order form. And then we looked at the concept of the state space form. MATLAB and Simulink have very nice tools about that. So we need to know what the transfer function is, and that's what I want to talk to you today. There is in here some guidelines for homework for next week from chapter 5 in here, and a computer assignment due on December 10, which is this example here. Quiz Tuesday, December 15. Okay, here we go. We have a system that is a piezoelectric sensor, and it's basically an accelerometer, and it's composed of this housing that you see here, like here, this, and this is attached to a device in here, yeah, that is going to measure the motion of this or the acceleration. So the way this works is it has a simple oscillator system inside. Inside this housing, there is this mass in here. And between the bottom of the accelerator and the mass, there is a piezoelectric material. This is a piezoelectric crystal. Now, piezoelectric materials are very interesting things in nature. They actually produce a charge when they are compressed, or when they sense the change of motion, or, well, compression in this case, they produce voltage. So that's why it's called piezoelectric device. So what happens is that if you get an acceleration from here, let's say an impulse over here, based on Newton's first law, the law of inertia, this mass is not going to want to move, right? And because of that, it will compress the piezoelectric material in a proportional amount to the acceleration. And then, of course, you have this damper and the spring that will bring them back to the original position. But that small voltage is produced here, needs to be measured. But because in piezoelectric materials the voltage is very small, then it follows that we need some sort of a device that will help us measure them. And that's where this comes in. This little circuit in here is the electronic part on this. And this device that you're seeing here, this is called an operational amplifier. Operational amplifiers are very interesting devices because they are not passive devices, they are actually powered externally. And their mission is, if you have in here a voltage, it will amplify the voltage in such a way that you can see it here. But the device is deliberately designed not to draw current from the circuit, because that would be a little disaster. Instead of contributing to find out, you would be, no, it doesn't make sense. The current has to be zero. So in this case, you have a voltage on this side, but you have an amplified voltage on this side. To be able to do this, we have device in parallel to this operational amplifier, a resistor, and a capacitor. So basically, this system that you're seeing here is composed of three things. It's composed of the mechanical side here. It's composed of this electromechanical transformation that has to happen to relate the motion of the part over here to a voltage on this side. So this is basically a transformer. A piezoelectric sensor is a transformer that transforms that mechanical motion into voltage. Okay? And mechanical motion into voltage. And this in here, once you have it in here, this circuit is going to amplify the signal so we can read it. So this is a simple electromechanical system, but you could see it has all the ingredients of a mechatronic system because it has a mechanical side, it has a mechanical electrical transformation side, and then it has an electrical side. And in this case, you have also an operational amplifier and a little circuit. So it is simple, to the point, and it has all the ingredients of a mechatronic system. What is the objective here? I already mentioned to you that in here you have the input voltage, acceleration in here, and in here we need to relate this input to whatever output we get over here. So if we measure the voltage across the capacitor in here, we will measure a relationship between the acceleration here and that voltage, see? But you see, here's where I am going to introduce you steady and slowly and precisely to the concept of the transfer function. Because the transfer function is a relation between the output that you have to one of the inputs. So if you need to write it down, that would be a very good thing to do. What is a transfer function? And you can write down, transfer function is a relationship between the output that we measure and the input of one of the inputs of the system. So it's always a one-to-one relationship. One output versus one input, right? If you have more than two inputs, then you are going to get more than one transfer function. But always a transfer function is the relationship, is the ratio, you may say, the relationship between the output and the input. Okay, so is it clear now what we are trying to do? This is the setup of the problem here. We have this piezoelectric sensor, and we are gonna measure it on this side. What to do? How to do this? That's our next challenge here. We need to build a model of the mechanical side, a model of the electromechanical transformation, and a model of the circuit. There's not necessarily any specific order that is better than another, but because we want to put these three parts together, we could proceed and do one, and then the second one, and then the last one, okay? So what we're going to do is we are going to build the circuit with the operational amplifier. This in here is this side of the device, and you can see we can build it using the currents here, or in your book also there is a method to put the zeros for the junctions. Nevertheless, this is the bond graph model of the circuit, which any way you do it by now you should be able to come up with this. Okay, but this operational amplifier, I want to have a little discussion with you about this, because you could say, Professor, but if this amplifies voltage and it gets a voltage on the side times some amplification and gets a voltage on the other side, should be a transformer, right? But the problem is that a transformer is a power conserving element, and this guy is not. Power conserving element means that if you transform a variable on one side to the other like a voltage, it follows that the current has to come into the picture too. And we are saying specifically that in an operational amplifier, the current is zero. So you see, this is it's not a transformer in the sense, because it's not power conserving. It's only amplifying the voltage, but it's suppressing the current. And in a real transformer, the product of current times voltage should be the same on both sides. That's not the case here. I just want to make sure that everybody understands that the operational amplifier is not a transformer. It is you may say, a half transformer, because the only one signal is not zero, but really we cannot use the transformer symbol nor the word in that sense, because one of the variables has been suppressed for purposes of what we want to do. So in this case, we could model it as a control source and have this model of the circuit in here. All right. Now, in this write-up, I have shown you a little demonstration of the conventional method. If you use the block diagram method and the bond graph method. So there's the derivation of the equations of motion for the circuit in here, and that's what this is. And this is the bond graph model, and I made some in writing the equations for that bond graph model, I made a comparison of the variables on the bond graph model to the variables of the equation 1, 2, which is this one right here, that one, this one. So just a little demo to show that the methods produce the same answer. In the case of a piezoelectric transformation, that one is actually a transformer because you have that the charge is proportional to the displacement in here, and dq dt, which is the current in this case, is the bdt, which is the velocity. So if you have a velocity on this side multiplied by the transformation on this side, we are going to get current on this side. And vice versa is true. You have the voltage on this side multiplied by this relates to the force applied on the device. So that's the piezoelectric transformation. That was easy. And now the mechanical side. So the mechanical side here has one junction for the ground velocity, one for the mass velocity, and then of course there is the relative velocity in between, and produces this spring and damper, following the same procedure as I have illustrated in the past. So here you have the bone graft model of the mechanical side. Here was an attempt to reduce the bone graft model, and the write-up also there is a proof how this bone graft model relates to the block diagram method, by the differential equation. So here's what you are to do. You need to assemble the whole electromechanical model, enter the bone graft model in CAMG, generate the differential equations in the Cauchy form, generate the differential equations in state space form, obtain the computer-generated transfer functions, which we're going to see a little later how they work, and in symbolic form, also in numerical form, and then you're going to do a test with the step and impulse response. What you would be pleased is that the computer does this automatically. Okay, so all you gotta do is put the right transfer function, the right system, and CAMG and MATLAB will do the rest. Okay, this is what to turn in as usual. Okay, so this is the assignment in here. So what it remained as right now is to go back to basics and find out how you can actually find the transfer function for an electrical system, how you can find the transfer function for a mechanical system. Because I told you that the transfer function is a relationship between the output and the input. So it follows that I could have a transfer function, this being the output over here and the input over here, or the transfer function between this and this input over here. So because the entire system is together, then we actually need to do the whole bone graft model of the whole thing. So right now we will have to do the bone graft model and then enter it into CAMG to find out this transfer function. But let's examine the transfer function in a little more detail with a simpler example so that concept is clear.